Hello, sorry about that. This is Dave Demaro. Welcome to the the latest Kitware webinar. The topic of today's webinar is building Qt-enabled web applications that use VTK. Sorry, not web applications, but Qt-enabled VTK applications. Again, my name is Dave Demaro. I'm a developer here at Kitware. I work on the VTK and ParaView projects. I'm joined here at Kitware by Jeff Baumus and Katie Osterdahl, who will be here to answer all of your questions via the chat interface in GoToWebinar, because I'll have my hands full running the presentation here and talking and trying to say things coherently. So let's see. So why might you want to use Qt along with your VTK application? At the heart, VTK is really a dedicated visualization library. It has very little support for user interfaces. There are no buttons or menus and things like that. And we try to concentrate on the visualization capabilities and let other people handle the rest of the infrastructure that goes around the applications that you build. We do have some minimal interfaces to a variety of different external libraries out there. You can learn about most of them in the VTK examples GUI directory for a variety of popular toolkits that we can interface to and build up, and you can use to build up applications that use VTK. The theme behind all of our interfaces is generally something that maps the VTK render window into the classes provided by the application library that you have at hand. Of these, Qt is particularly popular because, like VTK, it's cross-platform. It'll run on Windows, Mac, Linux, and a variety of other platforms. And it's quite polished. Here you see ParaView, which is our flagship visualization, general-purpose visualization application, where we've exposed pretty much all of the features of VTK within this friendly and easy-to-use Qt interface. So within this application, you can open up pretty much any data set, do any kind of visualization you might want out of it. And the interface that's presented in Qt makes it as simple as possible to really control all the complicated things that happen in a visualization setting. So VTK is good at data processing and making pictures, but it really needs help from something like Qt to be built into full-feature applications. So if you're going to go down the Qt route, what do you need? Well, we recommend VTK 5.10.1 right now. As you go further back or forward from that version of VTK, you may have more or less problems. And we recommend Qt 4.8. Again, same comment about the version capability. The farther away you go from that, the more problems you are likely to have. To use VTK, it's more or less essential that you use CMake. And for Qt, we really recommend that you use CMake as well to orchestrate your compilation process. If you're not familiar with CMake is a meta compiler. That is, it sets up the compilation process, but it doesn't actually do the compilation for you. And for that reason, you'll also need a C++ compiler available on your system for whatever system that may be. So a little bit of background about Qt. You can learn all about Qt and download it from qt.digia.com. Digia is the organization that is managing Qt's evolution currently and has been for the last release or two of Qt. Qt, like VTK, is a cross-platform framework. It provides really a full suite of software components, not just the widget set that we'll talk about here. And it has a dual license model. So if you're doing commercial development with it, you should use the commercial model, and if you're not, you're free to use the open source model, open source license version of the tool. It comes with a lot of really useful things. We'll see a bit of Designer here in use, and it also comes with a full-featured IDE called Qt Creator, which I've heard really good things about, which is pretty highly used here at Kitware. So first, again, I said if you're doing a Qt application, I recommend you use CMake to orchestrate the compilation process. And so in your project, you'll start off with a cmakelists.txt file, which looks something like this file right here. Start off by giving a name to our project. I'll put this at the top level of your source code directory. And then somewhere near the top of your cmakelist file, you'll say find package Qt. Now what that will do is tell CMake to go and look on your system for your Qt installation and make everything that Qt has available for the rest of your compilation units. After that, you'll call the include Qt use file to make that all available. And when you do the find package and include, one of the things that gives for you is a set of CMake macros that are very useful when working with Qt development, such as the Qt4 wrap UI macro, which we'll talk about in a little bit. You can find out all about what these macros are if you type cmake-help module find Qt, and it will list what this Qt4 wrap UI does and what the other macros are, and so forth. You'll set up your compilation, add an executable, whatever you call it, and then as in any other CMake-based project, you'll link that executable to whatever libraries it depends on. Like so, we'll link this basic Qt app to Qt libraries. So we'll start with a very simple Q application, very simple Qt application. Really, we'll just use top-level Q application, which is how, in Qt terms, the whole application flow is managed. This brings about the interface to the widget libraries, to application preferences, to help systems, etc. Many different things. The real guts of the program start when you call app.exec, which is what starts the interaction loop. Okay, so we'll try this, our first hello world in Qt space. So I have my code here. Starts off with a CMake list such as we've said. We have a find package Qt, and then we're making an executable, and we're linking our executable to Qt's libraries. And our C++ file is really the minimal, pretty much the minimal Qt application you can have. It's a main which creates an instance of Q application and passes the arguments, command line arguments to it. Creates the main window widget and populates that main window widget with a label widget. The label widget is the child of the main menu, and then it makes sure that everything is shown, and then it starts the event loop. So if I run CMake or CCMake or CMake GUI, and I'll tell it where my source file is, and here I have my Qt installation on my path. So CMake has already found where QMake is. Any of your CMake projects, this is the most important variable that you have. It specifies which version of Qt you want to use in case you have many of them installed on your system like I do. After we configure the project with CMake, we type make or open Visual Studio and build the solution, and then we end up with a simplest possible Qt application. Okay, so the key here is using CMake to orchestrate the fairly complex compilation which sometimes goes on in the background behind this. Okay. So that's all fine and good, but we really are interested in GUIs starting up, and so we'll do that by making use of Qt's many widget classes. So Qt's Q widget class is the base class for all the various widgets or almost all the various user interface elements that you might want to have in your application. Widgets, the base class is responsible for emitting and responding to events, signals, and slots. We'll talk about those later. And it's responsible for being able to paint some representation of the widget on the screen. Qt makes heavy use of smart pointers. Internally, thing that comes into play is that there is a parent-child relationship between the widgets and your application, And in general, the children of a parent are recursively deleted when the parent is deleted. So it is possible to programmatically define a Qt application. We could open up that Hello World application and start manually creating new widgets and linking them up in C++ code. But it's much easier if you can do you use visual design to do this. That is, you use Qt's designer and you lay out the Qt application's look and feel by placing widgets on the screen in pretty much the way that they will show up in your application. Designer, which I'll show you in a second, is a visual editor in which you lay out the widgets, and then it creates, when you type save or click save, it writes out a UI file containing all of the widgets that you've laid out before. The UI file is just an XML description, so it's just a text file which says what each widget is and where it is and how they're related to each other. And then in your CMake project, you use the macro Qt4 wrap UI, which will turn this XML file into compilable code. Okay. So I'll demonstrate Designer here. So what I mean by visual design, I'll start up Designer and then I'll create a main window widget. I've got a lot of clutter on my screen here. But let's see, here's my main window of this application that I'm designing. And I can say I can create the file menu, so forth. I can put buttons, drag and drop buttons onto the screen, and then I can control any of their applications within this this nice user interface here. And then when I'm done, I can say save, call it that, and quit out of here. And if I open if I open in a text editor that application, that file I've just created, I have this XML text file which lays out the relationship of all the various widgets which you will see eventually in that application. So give me a second here and let me try to reconfigure my screen here. I think I'm back in business here. Sorry about that. All right. So in a larger application, a slightly more complex one, might look like this one. So here we have a slightly more complicated user interface in which we have a main window and we have two regions on the screen. We don't have much going on in the file menu, but we've got a tree widget over here with a couple of different controls here. And as before, when we save, that will dump out our main window.ui file. And if we look at our CMake list file, we have a command here, Qt4 wrap UI, which will take in that UI file and produce a set, one or more compilable files, which eventually will be added to our executable and made for us. If we look at the C++ code, which is pulling this all together, we're making an application with a main window. And here, this is how we associate the output of Designer with the main window. But otherwise, it's very similar to the basic application we made before. This is, for curiosity's sake, this is the output of the compiled version of the UI file. It's just a header file with lots of different Qt boilerplate code in there. And when we make it and run the application, we end up with something like this. So here's an application that's not doing much of anything yet other than being an application with some widgets on it that are somewhat interesting. So how do we make our application, Qt application more interactive? And for this, what we do is we rely on Qt's signals and slots mechanisms. This is the command observer pattern as implemented in Qt, in which we have different instances of classes which can emit signals in their signal emitting functions, which are possibly received and handled by slots in other class instances, which have the handler code, which knows how to react to whatever signal they're given. We issue this type of code in our Qt application to connect the emitter's signal to the receiver's slots. And the way Qt implements this is with a bunch of keywords that you annotate your C++ code with, such as QObject, signals, slots, emit, and so forth, which after CMake calls Qt4 CPP, much like the wrap UI, it will take this annotated code and produce compilable C++ code out of it. So a quick example here of signals and slots here. Here we have, again, another CMake list file to orchestrate the compilation. And here we're using the Qt4 wrap CPP macro, which is taking in some of these annotated header files and making compilable source code out of it. And then we're adding the compilable source code out that's generated into our executable and creating the application like so. And if we look at the teacher class, this class does very little other than when it's created, it uses a Qt timer mechanism. I said before that Qt has a lot more than just widget sets in it. This is a very useful example of one. It creates a timer instance which registers which after a certain amount of time is going to fire a signal which is going to be handled by this teacher class instance's start course handler. And then when that happens, the teacher instance is going to emit its own tell signal. So here's the tell signal that the teacher class is going to emit, and here is the start course slot, which is going to happen after the startup delay. Likewise, if we look at the student class, it has a slot that is going to handle whenever it's called by calling its listen method, which you'll see here, and the listen method is really going to do nothing other than write something out to the console. So if I compile and run this with CMake, the teacher instance starts up and it waits 3 seconds, and then 2 of the students answered. So why did we only get 2 students answering here? Because we've created a teacher and 3 students, but only 1 of the student instances has actually registered to itself to listen to what the teacher has to say. Okay, so that's the general flavor behind Qt's signals and slots. We have instances which can fire off signals, and we have instances which can respond to those signals within their slots methods. Okay. So what signals and slots are really useful for is orchestrating, coordinating all of the various things that you'd expect from in a modern GUI. When a button presses, other code has to happen. You've got buttons which are coordinated with each other, which have to show the same results. So the signals and slots were really designed to allow the widgets, the many widgets which you might have in an application, to work together as a team, so to say. So using signals and slots, we can go back to our basic application we made with Designer, where we laid out a simple scene and we can make it do something useful. And we'll do that now. So this is really similar code. We're not doing anything different in CMake lists than we were before. And the one thing we're doing differently here in the main application is we're connecting a signal from the shape change signal, which is going to be emitted by the main window, to the status bar instance show message. And within the simple main window instance itself, we're adding some things programmatically to the QTree widget, which we showed in Designer. And we're connecting that tree widget's item clicked signal to this widget's instance shape changed. And then in the shape changed handler, we get that signal and we figure out what it actually was that caused this to happen, and we draw something different in the scene. So if we run this application, now we have something a little bit more interesting. Now we have the same application that we designed the UI before, but now, due to the magic of signals and slots, whenever the application is now responsive and changes as we'd like it to. Okay, so hopefully you get a flavor for what Qt gives you. Sorry I had to go into that so long, but I had to give enough background to continue on with what we need to know for the rest of the webinar. But the things you now should know how to do is how to make a Qt application, how to design a nice interface with Designer, and how to make widgets talk to coordinate with each other via signals and slots. So on to VTK. Some VTK background. Onto VTK background. VTK, you can find out all about it at vtk.org, and you can download it there and join the mailing lists and all that other good stuff that you might want to do from vtk.org. Like Qt, it's a cross-platform library. It runs on VTK, it runs on Linux, Mac, Windows, and a variety of other systems. VTK is really good at data processing and visualization, and it also has an open source license. In our case, it's a more free license than Qt's has. The last time I checked, Qt may have gone more open. But the last time I checked, it was still the commercial and open source split license model. So about VTK, the two major components in VTK are the data processing pipeline and the visualization pipeline. Within the data processing pipeline, we have classes called data objects, which hold generic data, most frequently scientific data, that is data which has some three-dimensional shape, and algorithms, which are instances which take in one or more data, or zero or more data objects, inspect it, analyze it, and then produce some one or more derived data objects. And these algorithms and their derived data, the data which they produce, can be connected into arbitrarily complex visualization pipelines to achieve pretty much any type of visualization effect you might be interested in. The other important portion of VTK is the rendering pipeline. These come into play everything beyond the mapper. The mapper is typically the last algorithm along the data processing pipeline. And the mapper's job is to take in the data objects and produce some set of rendering primitives, GL calls or DirectX calls or anything that you might have, which are necessary to draw some shape on the screen. Mappers are feed into view props, which is how the mapper's output is placed within some arbitrary world scene. And one or more view props feed into a renderer, which is responsible for drawing on a particular region within a buffer somewhere. And then the renderer, one or more renderers, feed into a render window, which typically interfaces with your operating system's window system to draw some window on the screen and so forth. And then interaction in VTK's case comes in through the interactor class, whereby the render window is notified of things like mouse events, keyboard events, and so forth. So again, you'll have some data processing pipeline which feeds into a mapper, which feeds into an actor, a renderer, a render window, and an interactor controls everything. And so you have one or more windows with one or more rendering areas inside them with one or more actors in them, which feed in, each of which gets usually one mapper to show the output of the data processing pipeline. So let's demonstrate a basic VTK pipeline to show you what we're talking about here. We'll just make a simple sphere procedurally, and then we'll show that we'll use some visualization, some processing to create glyphs to show the structure. So look at the CMake list file, and you see it's at the top. It's similar to what we saw for the Qt. Instead of saying find package Qt, we're now saying find package VTK, and then we're including what we find out of that, so we can have all the rest of the CMake macros, which VTK defines, available for the rest of our compilation. Then we're creating an executable with some set of source files, and then we're linking that executable with all of the libraries that we might need to link it. That is all of the VTK libraries in this case, rather than all of the Qt libraries we saw before. The VTK problem looks like so. We're using smart pointers here to make tracking of our memory usage more tractable. We're including the header files for all the classes we're going to use. And then we're instantiating these classes. A sphere source, which procedurally generates a sphere, a glyph, which is a filter which produces geometry on top of the input it's given, and then we have the rendering pipeline. We have a mapper and an actor for each of these two things we're going to show, and both of those actors feed into a renderer and a render window. So we have a sphere, and that sphere is being processed by the glyph. The glyph is being shown by the mapper. The sphere is being shown by the mapper, and these are all being drawn into a render window. So we'll make this class. And we'll start it up, and so we have our scene, which is the sphere, and then we're seeing the normals illustrated by these lines here. Note here that so far we have nothing interesting, no interesting interaction going on, much like we did in our first Qt application. In order to get interaction in our scene for VTK, we'll use events and commands. So this is VTK's observer pattern, which is comparable to Qt's signals and slots. In VTK, we have events and commands to fire messages and to handle them. So all events in VTK generally start off via the user, which go into the interactor, which feeds into the scene, like so. With this event, we get things like window repaints, and we also have a variety of widgets which can be placed in the scene and controlled with the mouse. And so using events, we can make our problem a little more interesting. We'll make a widget whereby we can control our visualization pipeline. Now our program now, we start off with pretty much the same set of pipeline elements. We have our sphere source going into the mapper, and those things are being rendered, but now we have a few extra ones. We have a 3D widget called a slider, which also knows about the events given to the program by the interactor class. And that slider widget is drawn by a representation. And the most interesting part about this is that the slider widget fires some events. It'll fire a VTK, an interaction event from time to time, and that will get handled by this thing called a callback, which we've defined up here. So we have a callback, which is a subclass of command. And every time this thing is fired, that is when the widget fires its interaction event, this bit of code will execute. So control will fall into this block here, and the first thing that the command will do is figure out who called it, and then it's going to do some processing. It's going to figure out from the slider representation from this widget, it's going to figure out where exactly it's set, called get value, to figure out what the value is, and then it's going to set some member of VTK class in the pipeline. It's going to change the glyph's scale factor. And at the end of the program, rather than just call render window render, instead we're going to tell the interactor to get ready. The interactor already knows about the render window and vice versa by this. And then we call interactor start, which is just like our Qt event loop start call. So I'm running Qt. Again, I have my path set up properly, so CMake knows where my VTK installation is. And when I run my basic VTK pipeline, I now have an interactive scene which will respond to user events, and when I change this widget, I can change the parameter of my scene. So we know enough now about VTK to start using it. We know how to display data, we know how to process data, and we know how to interact generally within the scene via the interactors and widgets for events and observers. So how do we put these two pieces together? So it all starts off with CMake. As before, we do a find package on Qt and a find package on VTK, and then we link our application to both sets of libraries. One thing that's important to watch out for is memory leaks. VTK and Qt have slightly different memory management models. Qt objects use reference counting. That is, a VTK object will be deleted when the last referrer to it calls delete on it, whereas Qt objects are generally deleted whenever their parent is deleted. So you have to be careful about this. Two recommendations I have for you are to compile VTK with VTK debug links on, and to turn on smart pointers, or to use smart pointers to create your VTK classes. So let's start up on we'll do the next exercise, in which we control a VTK pipeline from within a Qt application. So we'll use Designer and create an application which has 3 buttons. And then in responses to the signals that these 3 buttons fire, we'll it will call some code in VTK space. So again, here's our CMake list file in which we find and use Qt and find and use VTK. And then we have some set of classes that we process in Qt terms to create compilable code. And then we compile that and link to the sets of libraries we have. We use Designer to create a very simple application which has simply 3 buttons, an open, a filter, and a save button. And in response to the open button, we'll pop open a Q file dialog. So let's try this. So here's our CMake list file in which we find both packages, and then we prepare the Qt files for compilation and then compile everything. Here is the application which we have designed with Qt Designer. It's got an open button, a filter button, and a save button. Open button, a filter button, and a save button. And those things will be handled via the slots. So here in our application, we're connecting the clicked signal from the open button to this class's onOpen method. Likewise for the filter and save buttons. And we're also instantiating our VTK pipeline. So we have a VTK image magnitude filter, which is doing the bulk of the work we want here, but it's got a gradient and a shift scale, and they're connected together, so like in any other VTK application. So again, we have to include both the classes we need from Qt and VTK. We're using smart pointers to make sure we don't leak memory. And in our handler for the open button, we pop open a Q file dialog, which will let us browse the file system on the machine. And when we select a file, we'll create a VTK reader, and we'll open up the file we've been told about, and then we'll connect that to the pipeline that we have. Likewise, on the filter button, we'll tell our filtering data processing pipeline to execute. And on our save button, we'll open up a PNG writer VTK class and write that to whatever file name that we've been given it. So if I open up this, I can open up a PNG file, and then I can run the filtering, and then I can save it. And so we can compare here the results. This is the input. This is an image file of my children ice skating. And this is the gradient computation, which shows it's kind of like a simple edge detection filter here. So really all we've done here is once we've used CMake to put both components together, we've just called VTK execution in response to Qt, signals and slots. So that's all very nice, but what if we want to actually have our application make use of visualization? That is, how do we connect the render window in VTK into our Qt application? So what we need is really a rendering area, and the solution that we recommend is called QVTK widget. QVTK widget is part of VTK, assuming that you've built VTK with the VTK use Qt flag set to on. Once you do that, when you compile VTK, it will create a QVTK widget plugin shared library, which you can copy into your Qt installation to make this QVTK widget show up just like any other of the buttons in Designer that you might have. If you get stuck, you can go to this website, which has some recommendations about how to set up VTK and Qt properly to have this. What QVTK widget is, it's just a Q widget. It's a subclass of Q widget, but it has a VTK render window, and it has the code in there that knows how to paint the render window's output inside the widget drawing area. It also has a little bit of code inside which is helpful in connecting up the essential events from Qt space to VTK space and vice versa. So again, I've compiled VTK and set things up properly. So whenever I start up Designer, I have available to me, I have at the very bottom, I have a QVTK widget, which I can place into my application and manipulate as much as I'd like here. And then I can save this out, and it makes the same UI file that we've been seeing, which we all know now how to compile and so forth. So I've said that the job of QVTK widget is to hold a render window inside a Q widget. It also, the other important thing it does is connect Qt's event loop into VTK's interactor, so that the VTK world can receive things like mouse events and key events and so forth. So we can put a VTK scene in there, but so far this is just the render window itself. We still have to set up the renderer and the whole visualization pipeline that fits behind it. So I'll demonstrate here, and we'll add a QVTK window to the application we just designed so that we can see the files we're opening and saving. So if I open up the Designer file, I now have the scene consisting of the buttons. The application UI consists of the buttons and VTK widget inside the scene, none of which is populated or connected together yet. But if I look at the C++ code which connects these things together, I see that my main window sets up a visualization pipeline just like we saw in our earlier examples. We have a filter button, save button. We have a magnitude filter, a gradient filter, a scale filter, and we end the visualization pipeline sending into the QVTK widget, which is part of our UI designed application interface. So we send the renderer that we created up here as part of the visualization pipeline into the QVTK widget, and then we get a hold of the render window's interactor style, and we connect that up to the Qt space. Now in our handlers, in our slots, not only do we execute the code to open up a file, but we also add the output of that reader into the scene, into the visualization pipeline, and then we tell the VTK widget to update, or in other words, to render it. And same thing with the filtering and saving. So now we have a scene, we have an application, I should say, which can open up a file and then show us the file via the Qt interface. We can apply the processing like before, and we see the visualization as it's happening, and then we can save the processing, save the result as before. But we have feedback in the viz space that is much more helpful to see what's going on. So now we know how to link VTK and Qt together. We know how to control VTK from Qt and how to show things in VTK space within our Qt application. But occasionally it's important to do the opposite process. So we have been controlling VTK from Qt, but in some cases, for instances when you're using VTK widgets in the scene, you want VTK to control the Qt scene. The way you do that is similar to the way you tell VTK what to do from Qt, is that you use VTK's commands, in VTK commands, that is the things that respond to events. You tell the commands to trigger events that change the GUI elements. So you can have GUI elements that change things in the VTK pipeline, and you can have VTK pipeline events changing the GUI. We'll demonstrate here quickly. So in this case I did not use Designer, but instead I coded up everything manually here. But we see similar command that we saw in the pure VTK interaction example. And in our callback command, which is called from a VTK slider widget, we are going to set the resolution. Let's see, slider widget color, and I'm calling the representation. So this is the exact same code as before. Let's see what our pipeline looks like. We create a renderer, and we put it into the Qt VTK widget, get a hold of the interactor. We set up our visualization pipeline with a sphere source, a slider widget, and the slider callback. We draw the scene, and then we connect the Qt widget for changing the resolution to a slot to handle the value. And in response to that, we tell the scene to render itself. And in the callback, in the set resolution, okay, I see here. Here's the handler in VTK space. So whenever the Qt widget slider is changed, sorry, the VTK 3D widget slider is changed, it calls view set resolution. So this is calling back into Qt space, which is updating the Qt scene, and likewise the Qt scene feeds back into the visualization pipeline by calling a set value here. Run CMake. I've got my path set up, so I find my Qt installation and my VTK installation. Configure and generate. Now I have make files. I run make, and then I have this full-featured scene where I have a Qt world, Qt widget which can control the VTK scene, and the VTK scene can update the Qt scene as well. So what I'm saying here is that this Qt widget is connected to this VTK widget because of we've connected our signals and our slots to our events and commands correspondingly. So in that instance, I did the connection manually. But if you do a lot of this, you want to cut down on the boilerplate code as much as you can. So I recommend looking into the VTK event Qt slot connect class, which is part of VTK, which really just instantiates the boilerplate command event code that I I showed you manually into a few calls into VTK commands, and it cuts down on the size of, it cuts down the amount of typing you have to do to set up a nice interaction between the VTK and Qt space. So that's the bulk of what I had to say about how to connect VTK and Qt. We know how to compile applications that use both libraries and make all of the things that they provide available. We know how to control VTK from Qt space. We can create a visualization pipeline and then control it in response to Qt events. We know how to use Qt VTK widget to show visualization results within our Qt application. And we know how to connect VTK events back into Qt space so that we can have correspondence between the things we see in the VTK land and the things we see in the widget space. I should say a word about there are a few widgets out there that make things make designing visualization applications possible. If you do a lot of this type of work, I recommend taking a look at the Common Toolkit, which is a project that we at Kitware are part of, and what it's meant for is providing widgets and a whole bunch of the rest of the glue that is really useful and reusable in medical visualization applications. So it's, again, open source. This is an Apache license. You can go to commontk.org, look at that website. In particular, look at the widget set. There are 60 or more widgets, many of which are tailored for bringing Qt and VTK together, things that you might do, or rather than code up these widgets yourself, it's better to go with a tested version of these widgets. So I recommend you take a look at Common Toolkit. And that is all I had to say, really. You can learn more about VTK at vtk.org. The mailing list is one of the best resources available if you're doing any kind of VTK or Qt coding. There's Qt mailing lists that are very helpful, and the VTK mailing list, which I and Jeff and Katie are all on, and most of us at Kitware are there. Also look at the VTK wiki. In particular, look at the examples under the wiki, which has a whole slew of example code to get you started in VTK and some in the VTK Qt code. And and there's always, if you really get stuck, you can look up the Kitware support, and we'll be glad to help you get by whatever problem you have. Thank you for your attention, and I hope you've learned a lot. And I'm sorry if I went too quick for this. This is my first time giving this material, so I think I went a little bit too long. But thank you very much. And that will be it if there aren't any questions. So in response to Eve's question, yes, the Python is available. We have pretty decent support for PyQt and SIP. In VTK. I haven't used them myself recently, but ask on the mailing list, and it does, using Python and Qt and VTK together are really a good way to get things going really rapidly, especially prototypes and so forth. I'm going to try to put up the source for these examples up on the VTK wiki. I mentioned before the VTK examples. Many of the examples I started from this material from came from there, so it's definitely enough to get you started. And I'll see if I can put the rest of the stuff up there as well. From the question from Larry Kellogg was, can you place a Qt widget inside a VTK render window? I have seen people do that. If you ask on the mailing list, it's most likely that Clinton Stinson will respond. I have heard of people doing that before, but I have not tried it myself. But yeah, I remember seeing scenes of like a Doom-like setting, this third-person shooter game where there were Qt widgets inside a 3D world, and so that is definitely possible, but I don't know the specifics of it offhand. But if you ask the mailing list, someone will likely help you.